It's my honor now to introduce Dr. John Edwards. As I said, I first met John when he was at AWE. He actually came over and joined Lawrence Livermore into the Weapons and Complex Integration Directorate in 1998. Actually, I believe, and Alan could correct me, I believe it was called something different at that point in time. At the labs, we tend to change names always, but effectively that is what it's called today. John was a leader, even at AWE, in the ICF community. Came to Livermore, continued that trend, and currently today is the actual Inertial Confinement Fusion Program Director in the Weapons and Complex Integration Directorate at Lawrence Livermore National Laboratory. He's responsible for the ICF's program's direction, looking at what are the needs of the Stockpile Stewardship Program and how can ICF interact with that. And with that, the last thing I'd like to say is he actually got his PhD in 1990 from the Imperial College of London, and he is author of more than 100 papers. And so let's welcome John Edwards. Thanks.
Okay, well, good morning, everyone. It's really a pleasure to be here, and it's quite a pleasure and a bit of a surprise to see so many people here in this fellowship program. And first I'd just like to say congratulations to you guys, because this is pretty hard to get into, but it's really setting you up for potentially, as Ralph said, future in the national laboratories, which for me at least, and many of the people that work at the labs, is incredibly exciting. And there are many, many opportunities, scientific opportunities there, which perhaps you'll be able to take advantage of in the future. And we really need that help. So congratulations to getting into this program, and you're going to have a wonderful future. So what I'm going to do today is I'm going to talk about what ignition is and how it sort of a little bit how it fits into what we do. 10 years for the program. Well, here's something that lasted 20 years, actually 20 plus years now, and it is the Stockpile Stewardship Program. So a group of people towards the end of last year, got together in Washington to celebrate this. Now, this all came about at the end of testing, as you all know, and it wasn't clear exactly what was needed and whether it would succeed or not. But it's basically been a roaring success, and it's required a huge amount of innovation. There are many challenges that had to be overcome, but nevertheless, it was a big success. And the things that Ernie Moniz talked about, Kerry talked about, the lab directors talked about, they focused squarely on the science of what we are doing and the continual need for innovation to overcome the challenges that we faced during that period. But that was 20 years ago. We're now looking into the next 20 years and beyond, and we're asking ourselves the questions, well, things are going to be very different. There'll be new challenges, perhaps even greater than the challenges we've had before, and a new generation of people to help get through that, to understand all this stuff. One of the things which has been part of this, the stewardship program, is our big facilities, like the National Ignition Facility and the Ignition Program that I'm going to talk about today. And it really is, ignition itself is a massive grand challenge. And like all grand challenges, they're a journey. They take a lot of innovation, they take a lot of persistence, and above all, patience and time. And that last one is one that I emphasize continually to our friends in Congress. Isn't going to just happen by falling off a log. So what I'll do is I'll just take you through briefly what ignition is, how it kind of fits in, where we are at the moment, and then tell you what the remaining challenges are, we think, and how we're going to go about addressing them. So ignition is where we try and take DT, hydrogen isotopes, and compress them up to very high densities and temperatures and get them to start heating themselves and burning and eventually ignite. And pretty much every scheme works like this. You implode some fuel, DT fuel, and try and generate a very small hotspot. So put a small amount of energy into a small region, get it very hot and dense, get it burning, and then allow it to propagate outwards. Pretty much everything looks like that. All the work comes from the imploding shell to heat the center. Now, if you do it well enough, the center gets very hot and you get fusion reactions, DT fusion reactions. The 3.5 MeV alpha particle, helium nucleus. If the conditions are right, if you have enough stopping power, enough rho R in the hotspot, it'll stop, it'll heat it up, and that fusion power, because the reaction rate is so sensitive to the temperature, it'll accelerate itself. And if you do it well enough, of course, eventually it'll sort of run away. But it's a race, and it's a race against things that are trying to cool it down. So it's trying to radiate away, and it's trying to conduct energy into the walls. Now, if you look at those relationships there, you'll notice that the fusion reaction and the radiation reaction there are both n squared times some function of temperature. So if you say, well, actually, at some temperature, because the n's just drop out, those are sort of balanced. And that turns out to be about 4 keV, 4 kilo electron volts. So that's an important number. Once you get above 4 keV, then your fusion heating all by itself, if it's right, it will outweigh one of the cooling mechanisms. So then all you've got left is you've got to beat the other one. So you just need enough temperature rise and enough compression from the outside that you can beat the other one. And what people don't realize is that quite often is that what's happening in here is not just the temperature rise, but the density rise as well. And the density rise is because all the energy conducts out into a thin layer and it ablates material off into the hot spot. So the density rises as well. And once the density rises, because this guy over here isn't dependent on it, but this guy is, and the temperature will actually ignite. So that's a critical piece, getting that fuel to that hot spot to form. But it's quite difficult. It's really quite difficult. Then if it ignites, then the alpha particles, it basically runs away. The alpha particles propagate out into the surrounding fuel, and it's basically a thermonuclear burn wave. And it's very straightforward to work out how much energy you would get out of that, and it's given by that simple expression up there. And on NIF, that would be about 25%. So that's about, if everything worked perfectly, it's sort of a 20 megajoule system, or about a kilogram of coal, something like that. Today, just to tell you where we are, we sort of say, well, we're about factor 2 from ignition. It's actually a little closer than that. What we've demonstrated, so a couple of important things. Firstly, you'll notice we got temperatures high enough to start beating some of the mechanisms. The densities and the pressures are just a little bit on the low side. Sort of roughly factors of 2-ish, a little bit less on the pressure. The most important thing that we've demonstrated, this is the first time we've done this in the laboratory, is that we've actually demonstrated this heating process is starting to happen. And it's starting to happen at about a level of about a factor of 2. So it's amplifying the yield by about a factor of 2. So that's a critical step for ignition to happen, and we're starting to see it happen in the laboratory. So that's kind of important. Now, you can think about how much energy you need for ignition. You say, okay, well, it's just the mass of this stuff, however much I need, times the temperature. So it's just rho r cubed times the temperature. And if I took you through a little bit of simple thinking about the power balance we just saw, you can rewrite that in terms of the expression at the top left there, and you get something with rho r cubed, temperature cubed, divided by the pressure squared. Now, it turns out that if you go through the power balance arguments, you need a certain amount of rho r to confine it and stop the alpha particles, a certain amount of temperature to get heating rapid enough for ignition to happen. So those are kind of fixed, roughly fixed. You don't quite know how much of each you need, but you need some combination. So that basically comes down to, well, the energy you need is just how much pressure you can get. And how much pressure you can get depends on how much convergence you can get. So if you think about something like the National Ignition Facility, it was sized based on basically what pressure people thought they could achieve through high convergence implosion, based on experiments done many, many years ago, 20 or 30 years ago. That's basically that's kind of how it got sized. And then they threw in a little bit extra, maybe not enough, to compensate for any things that they got wrong. So then you can ask, well, what else can you do? All right, you need high convergence implosion, but are there ways you can get around that? Well, one is you can just make more energy, get more energy into the fuel. So that relaxes that requirement. Or you can try and go after the losses. And the losses, well, not much you can do about the radiation for something this size. So you think, well, all right, let's go after that one, the electrons. You can magnetize them. Obviously, you can perhaps reduce the losses like that. So there's two things you can do. You can either put more energy in, or you can try and reduce the losses. And so the reason I go through that is that basically is what the ignition program is today, the National Ignition Program. So I'm going to talk about X-ray drive, this thing here on the left, but actually there are kind of three things that we're looking at very actively in partnership across the various laboratories. So X-ray drive that we'll talk about. The reason we look at X-ray drive is it's the most mature and it is the most stable when you try and implode it. It just is very, very stable compared to the other approaches. But it's not that efficient. You've got to heat this hohlraum. So a lot of the energy actually doesn't get into the fuel where you really want it. So that means you need high convergence. Remember, energy 1 over p squared. Not much energy, another p, a lot of high convergence. Okay, get rid of the get rid of the hohlraum, put the laser directly onto the fuel. Well, then you've got the laser directly on the fuel. You've got to get the laser beams really very, very uniform, and you've got a lot of heat right there. You don't want to get it hot. But you can get a lot more energy on. You don't need as much convergence. That's easier. Not as much amplification of errors. Challenge is, when you take all the other things into account with being more unstable, it's equally hard to work at the lower convergence. So there's no free lunch there. But there's another approach which is worth looking at, and that's at the omega laser. So they say, okay, well, let's get more energy in and put in a magnetic field, and that's basically what we're trying to do with the big magnetic machines at Sandia. So what they do there is use a cylinder with put a current down the cylinder. You get a B field, and you implode the cylinder. But before you do that, put an axial magnetic field down the fuel in the center, heat it up with a laser, so you don't have to rely on the implosion doing all of the heating. The magnetic field stops the electrons taking heat away, and as you compress it, it gets more intense, and eventually it actually traps the alpha particles as well. And in fact, we've demonstrated that. So here's a very scalable system. That's the attraction to this. It's very scalable. Get lots of energy in there, so you don't have to work at high convergence again. And all of that, all the elements of that look like they work. The big challenge there is that as you're putting the laser in, it looks like there's a lot of mixing getting in other high Z materials. And the high Z materials, it's such a long implosion, it radiates the energy. So that's the big challenge for that approach. But nevertheless, and there are variants on that. So that's basically what the ignition program is at the laboratory at the moment, with a very active set of work that's being done over the next 5 years or so. So I'm going to talk about this one. Happens predominantly at the National Ignition Facility, but of course it's a big international concern, a lot of big national contingent. If you've never been to the lab, kind of a square mile, there's the NIF San Francisco Bay in the background there. Here's the NIF inside. You've probably seen pictures like this before. There's great YouTube videos on this, by the way. What people don't realize is that you can kind of see the efficiency scheme here. Now, admittedly, the laser is actually relatively old technology. It's not modern technology, which would be a lot more efficient. But nevertheless, there's about 4 megajoules of energy stored in the capacitors. You draw that off the grid. Then you put that into flash lamps that put the energy into the laser slabs, which are going to amplify the laser light. And you get about 10 megajoules in there. The laser light takes out about 5. You convert that into blue light from red light. You get about 2 megajoules at the target, of which about 150 kilojoules gets into the capsule, and only like 15 to 20 kilojoules gets into the fuel. So it's not the most efficient system in the world, which is why we look at these other potential methods to get more energy into the fuel. Nevertheless, that's kind of the bottom line. With modern technology, the efficiency here would be very much better. But nevertheless, laser bays, laser glass, so much glass that you have to pour it, polish it into wonderful slabs. Innovation, not even innovation number one, probably. The only way that NIF actually can function today is because of huge advances in the understanding of the damage to optics. It's the only reason that it could possibly function. And that's taken many, many years to develop. Patience, a lot of scientific experimentation. And what happens is, you think about this, there's a huge amount of energy coming down these laser beams at like 10 joules per centimeter squared. So these are things, regular glass would just be totally trashed on this stuff. And the problem is that small imperfections or damage sites or whatever you have on the glass surfaces, that's where the laser will interact and it'll actually start to damage there. So there's an awful lot of work went into how you process these optics. And what you're looking at here is the number of damage sites against the fluence. So this envelope, this blue envelope here, that's on a full power shot, that's kind of the fluence distribution you get on a shot. And you can see if you went back to 1997, to optics in 1997, the number of damage sites you would get from here is tens of thousands. It would be totally impractical. You could not do it. You'd be replacing the optics every few shots. So there was a large, as you can see, over many, many years, they've basically driven that down by understanding, a lot of it's in the processing, how you process and clean the glass and things like that, and manufacture the glass. So today, we're down pretty much to a place where it's not entirely zero, but it makes NIF possible. In fact, NIF's firing 400 odd shots a year here, which is pretty substantial. So number one, all goes into the target chamber. That's what it looks like today. A lot of the blue stuff there is just blue paint on concrete, which is to moderate the neutrons, laser beams going in. It's quite an engineering marvel. This is where all the final optics are, where the light gets converted from red to blue light. And inside the target chamber, 10-meter target chamber, target positioner there on the right-hand side, it's over, this thing's like 10 meters long. It's holding it to 25 micron stability. And the whole building is an earthquake zone, has to be isolated from the rest of the land. I mean, it's remarkable, but it works. It's absolutely remarkable. The target, well, it's got to be cold. So the fuel in there is in a layer. It's in ice. It's frozen. So it has to be cold, minus 20, 290 degrees. It's 17 Kelvin. And so you have to have shrouds around it to stop the room light just blasting the layer of ice, DT ice away. So targets, here's another, simple thing, experimental physics. These are targets from the 1980s, and you can even see the quality of the image there. Pretty simple thing. This is an ignition target today. And it hides a lot of the engineering detail. This took several years to develop to the point where we can do these things routinely. I could talk for an hour about this all by itself. There's the components blown out, and probably this is probably a simplified version, but every single one of those components is required in there to make this function in the environment of the NIF. That's what we're trying to implode. This is an X-ray picture of the capsule right before we shoot it, and you'll have to look very carefully, but this is a solid layer of DT right on the inside there. So that's, this is 2 millimeters across. It's, human hair's width here of DT that we're trying to implode. It's capsule. That's why it's so hard. It's got to go that far. What you're looking at there, you're looking at an X-ray picture from the DT fuel as it's starting to burn in the middle. It's a lot of energy, so unfortunately no part of the target or other piece is reusable. And this is kind of how we try and do it. So we put laser beams into what we call a hohlraum, which is this typically gold. It's this high Z container that's high Z so that the X-rays don't get out very easily. And we put the power in a very special temporal form so that we keep the fuel cold as it's going in, and the big pulse at the end accelerates it. And the laser beams, this is a cylinder, this is a sphere, so we have to put the laser beams in special places to try and balance the radiation field, in particular because there's obviously no radiation field coming from where the lasers go in. There's a big hole there. So you have to be clever in how you balance that. So that's a big challenge. Getting that spherical in a cylindrical system like this is actually quite challenging. The other thing you have to worry about, so other than driving it spherically like that, is hydrodynamic instability. And any small imperfections on the surface can amplify, break up, and if they were this bad, then it won't work. Turns out, actually, that was one of the things we can calculate really quite well. Turns out all the hydro pieces, we've done lots of experiments, we can calculate this quite well. So we can manage this effect. This would be bad, but we're able to manage it quite well. So this is kind of how we look at where we are today with ignition. And it's a plot of yield against basically the Lawson criterion. It's sort of the quality factor of the implosion. And it's right. So if you look at it at the moment, I tell you how much energy we're producing. We're sort of at this thing of about 0.6 or so. You need to be at 1 for the thing to ignite. The important thing, as I said, is it's actually the fuse is starting to light, but it's just not quite robust enough to get the rest of the system to light or get the hotspot to take off. And the question of this is, kind of what's up. And interesting, if you take this number here, the energy you need for ignition, we talked about this earlier, is sort of 1 over this parameter squared. So you say, okay, well, if we're at 0.6 squared, 0.3, 1 over that, 3. So if you could do nothing else, we'd be short by about a factor of 3 in energy to get this. So if you just scale it up by the cube root of 3, just to scale it, it would probably ignite. But it started over here, by about a factor of 100. So that gap in how much energy we need is gradually shrinking and shrinking. The question is, can we shrink the rest of that gap? And to figure out what's going on, you need diagnostics. So NIF has a large number of very high-quality diagnostics, state-of-the-art diagnostics. There's 50 or 60. It is probably the best diagnosed HED facility anywhere on the planet. And that's a combination of the size, because it's large, you can get good resolution, and because of the quality of the diagnostics. All of the diagnostics are based on test site diagnostics, but again, they benefit from many, many years of technological advancement. So it's interesting, when the NIF chamber went in, it was actually one of the cranes from the test site actually was brought to the site to put the chamber in there. Now, as a result of all of that diagnostic development, there's a huge amount of information we now know about what's going on in these ignition targets, way, way more than any of the other approaches. It's just more mature. We've spent more time looking at this. But it takes time. You can see the timelines there. It takes kind of a year to get these new techniques in. But it's an enormous amount of information, but it's not yet quite enough. There are still some knowledge gaps that we have. And I won't talk through all of this, but all of that goes into telling us what we think are the major obstacles. And this is it. This is kind of what we think is the major thing going on at the minute. So if you take that and you put it into our best simulations, run it all the way through, we think there are two things that are going. One is, I talked about a little while ago, it's very hard to drive this thing spherically enough the whole time. It's got to be better than 1%, better than 1% uniform in X-ray drive. That's one of the issues. The other is that you have to support the capsule in some way. So we call them these engineering features, and it happens to be this thin membrane, which is 30 nanometers, so it's molecules thick. And as it blows up, there's a contact ring first off where it contacts the capsule there. But as it blows up, it puts a little wobble on the capsule. So as it implodes, it's unstable, and you generate this little aneurysm. And what you're looking at in the middle there, it's like a dental X-ray of the capsule as it's imploded. And you can see for a couple of things. One, it's not round enough, obviously, because it's got a long way to go. And you can see the big marks, gashes, if you like, aneurysms generated by these support. We call them TENS, supports. So if you put all that in, our diagnostics are excellent up to sort of about this point, to almost the end of the implosion. But once you get down here, everything gets a bit more murky. And it's because it's very, very harsh environment to diagnose. That's one of the focuses that we have at the moment, is trying to close the knowledge gaps of what's happening down there. That's one of our very big simulations that I'll talk to you about a little bit more in a minute. The first one of those took a year to run, to figure out how to do and run. It's absolutely state of the art. There's a lot of stuff you can read about it, but it's very, very challenging. And it didn't just come out of anywhere. It came out of many years of advancement, so yet more innovation, both in computing capability, but also in algorithmic development, and what eventually, going from the early days, from actually the start of the stewardship program, all the way up to what we're able to do today. None of this would have been possible without actually many people like you coming in and working on stuff like this. So here it is. This is this big 3D calculation. On the left-hand side is kind of what you would like, and in the middle this is what we think is happening from the X-ray drive asymmetry, because we've made all these measurements. And you can see that's not too pretty. It basically forms a donut. And on the right-hand side, if you put all the other perturbations, the capsule 10, you can see not only is the asymmetry not very good, but these features here from the tent actually come in and destroy the hotspot. So there's no way that's going to work. And we think that's the main problem. There may be other issues that are going on, but fixing those two issues at the moment are our main focus. It's not actually obvious exactly how we do that. So here's a very visual way. This is real data in the middle looking at the hotspot, and it's looking down the hohlraum axis. Okay, and so what you're seeing is this donut. If you look from the side, you would figure out this is actually a donut. So that's the image that I showed you pretty much on the previous page. And it's kind of not that pretty. It's got some asymmetries from some other things. But these are not all the implosions are quite that distorted. Some are quite a bit rounder than that. And the better ones are the ones that perform somewhat better. So what are we going to do about that? Well, two things first. One is so we've got to work on how we hold the capsule, and we've got to work on the hohlraum piece of it, making things more symmetric. So the capsule, well, why don't you just take the whole support away? And well, the problem is that this tube is actually. Bear with me 1 second. Let's try again. There you go. So taking the support away probably won't work. Now, life can be cruel sometimes. It turns out that there are cryogenic pumps on the chamber that have a frequency of 60 hertz. The resonant frequency of this, any guesses? 60 hertz. Beautiful. So not going to work. All right, so you've got to do something to stop this, right? And you would think, well, that's pretty simple. Just put something in there to put a wire across it. So that's what they've done. And then you go off and you do offline experiments like this one at the top here, where you put the test target in, you backlight through it, look at the imprints that you get. Some surprises there, actually. But if you can stand this thing off far enough, it would work. It would probably work. It would be a much better capsule support. Okay, great. So then you put it in the hohlraum, and it's kind of like this up here, up at the top left there. Well, so there's a wire going through the hohlraum. Put glue on the piece here. Cool it down. It's going to shrink. All right, so the glue's going to leak. Maybe the glue doesn't hold up, so it's going to leak. So the engineers, they thought about that. So they said, okay, we're going to put windows on the outside, so when that happens, it'll be all right. But when that gives, it turns out you lose the support there, and it sinks. So you just don't know how reproducibly it's going to sink. Oh, okay. And then occasionally, they detach here just because of the stresses that get involved. So it's not simple. Even just putting a big tube on there is not simple, because in the cryogenic environment, stuff shrinks and the stresses get different. So when you've solved the problem in one place, it doesn't mean you solved it somewhere else. So it really does stress all of the engineering and the ingenuity. The other thing that is great about this picture is, we draw pictures of this stuff with straight lines here and there as a designer, and you put them in calculations straight. I mean, it's nothing like that. I mean, you look at this fiber. It's this 10-micron fiber tube, which is putting DT fuel into the capsule, and it's just bent like that, being supported. So this is an enormously challenging problem. And there are many other ideas that people are looking at. And everybody says, why don't you drop it? Why don't you levitate? Why don't you do this? Why don't you do that? And so people have thought about all those things. And actually, the only levitation technique that might work is magnetic levitation. And so a couple of the engineers, actually from all over the site, got together and came up with a scheme that would probably work. You need a thin layer of high-temperature superconductor on the outside of the capsule. And they've managed to do some coatings on flats. So it's not for the near term. But again, it drives these big innovations. So the hohlraum. Last thing I'll talk about. The hohlraums they fall into these two different sort of categories. The hohlraums we've been using are these things on the left. And so this is just a cutout of what the beam path might look like. And they're what we call LPI, laser plasma instability dominated. And what that means is that the laser light propagates into the hohlraum and it generates waves. And the light scatters off those waves, electron waves, ion waves. And all the scattered light, if it's intense enough, scatters off waves and generates waves. And it's incredibly difficult, and it's very, very complex physics, extremely complex physics. It's not going to be predictable anytime soon. So that's kind of what we've been living with. And there's a reason for it. The reason is that when people were concerned about, one of the big concerns, remember, convergence ratio and energy. A certain amount of energy that we could build in a viable machine, and a certain amount of convergence ratio, and you're trying to balance those two things off. So you want, basically going from where we were, which was sort of the omega class system, 20 kilojoules or something, up to 2 megajoules is a very large step in technology. So you want to keep that to a small amount as possible. So the energy was really a premium that people were thinking about. And a lot of the energy goes into the hohlraum, so the smaller the hohlraum, the better off you are. So there was a big drive to make that as small as you could and still drive the thing spherically. That's basically the trade-off. Understanding there would be these laser plasma instabilities, one of the big unknowns. We knew it'd be there, didn't know how much. And the only thing that people were concerned about, they thought about it as a net energy loss. Didn't really think about it as generating other issues. And it generates issues in controlling symmetry is the thing that we learned. That was one of the big things that was, it was considered, but it was the extent of it was missed. So to be able to work with the hohlraum that small, what you end up doing is you end up putting a gas in the hohlraum here, and that actually taps the wall, stops the walls from moving in, as there's not much wall motion. So that's kind of the idea. If the wall moves in too much, like it does on the right-hand side, then the laser beams have got to propagate through the goal, all sorts of other things, and it just makes it. At the time, it wasn't thought that would be a good environment. But it turns out that actually the environment on the right is much more benign than the environment on the left. So if you go to much lower densities, laser plasma instabilities, they don't like, you can kind of sum it up in a couple of things. Density is bad, temperature is good, long scale lengths are bad. That's pretty, and high intensities, those are all bad things. So the only thing we really have control on here is essentially the density. So you can lower the density by taking out some of this gas, but then you get this more wall motion, and you get a more complicated geometry. So you're trading complicated physics for more complicated geometry, but it's rad hydro. And rad hydro is kind of what we do, what we think we can calculate. So the direction that we're moving at the moment, and this is still we're still in the middle of this, so is to eliminate the horrible laser plasma part of it as much as we can, and get to these hohlraums which are better. It turns out when you do that, you get much more efficient, so you don't have all this energy loss. So that's number one. So you can make it bigger to start with, which was a plus. There's a lot of energy tied up and lost on the left-hand side, that was not appreciated beforehand. Turns out that if you make them big enough, you can generate them, drive the capsules spherically enough, and it turns out they are more predictable. So it comes down to, at the moment, a simple question. So if you make hohlraums which are much bigger, or the capsule which is smaller, either way you can kind of look at it, make the geometry simpler, it turns out that you can drive capsules spherically enough, probably. We can't say for certain we can do it yet for an ignition-like capsule, but you can, in principle, drive them. The question is, can you get something which is big enough that it will ignite if you drive it in an ignition-like way? So this is at the bottom left here. It shows, there's no scale on it, unfortunately, but it shows the radiograph of the capsule coming in on the hot spot. And it's only at about convergence ratio of 20, but it would be, based on all the measurements we've done, it should be good enough up to convergence ratio 30. But it's a small capsule inside the hohlraum. It's about 50% scale. So the question is, can you make the capsule big enough and still maintain the symmetry? And this is kind of a summary of the last thing I'm going to talk about. This is kind of what we're looking at. So think about it this way. NIF has, another way to think about it, NIF has roughly 2 megajoules, 500 terawatts. So there's a certain size of hohlraum you can drive, which will reach the temperature you need to drive a capsule for ignition. Simple as that, certain size. Okay. And then you ask the question, well, if I put a small capsule in there, kind of think I can drive it spherically, can I gradually make the capsule bigger and bigger? Can I make it big enough I can still drive it spherically and get the ignition conditions? And it looks like the answer is right on the edge. We're not quite sure yet, but it looks like it's right on the edge. So the question then is, well, all right, what do you do about that? If you're not quite there, if you can't quite do it, and these experiments are ongoing, what do you do? Well, firstly, you're trying to figure out what's really going on in the hohlraum. Is the hohlraum, why are we right on the edge? Is it because of the hydrodynamics in there? Is it because of the gold bubble? What we call this is gold plasma expanding into the hohlraum. Is it because this beam is getting intercepted by that? Is it because it's just getting denser and we're losing control? What's limiting our ability to do this? The second thing is, suppose you can't quite make it big enough. Well, are there other things we can do with the hohlraum? And there's a lot of activity thinking about different hohlraum designs. One that's very simple in concept is the reason why the material from the hohlraum just blows in is because it's very dense, gets very hot, and there's not much density inside, so there's a big pressure imbalance. Just change the pressure of the wall. So one way you can do that is you can make walls that have these foam liners. And we've done some experiments actually like that, and they kind of behave in a similar way to what we predict. On paper, they work great. So on paper, you can take a hohlraum like this up here, which is just a solid hohlraum which closes in where the beams hit, and you can delay the closure dramatically. And actually, it improves the situation hugely. But again, it's a big technological challenge for the target fabrication. It will take at least a year to kind of work through to see if the concept will even work the way that we think. And remember, foams are not these nice gases that you simulate in your codes. They're actually fibrous materials with big gaps in between them. So that's to explode, homogenize. You'd have to do it uniformly, reproducibly end to end. So it's not in design space, it's wonderfully simple. In reality space, it's of course not quite so simple. And then better visualization of what's going on in the center, and we talked about that earlier. So that's the last part of what we need to do, is understand what's really happening at stagnation to verify that our simulations with all those inputs are exactly as we think. So that will take a number of years to work through that, and we'll see at the end of that where we stand if there are any other issues that have come up along the way. But we will have been able to drive things, I think, spherically. The question is, can we actually get them big enough at the scale that we need to get them to ignite? Isn't going to happen without a lot more innovation in both the diagnostics here and the techniques and the ideas. And most likely, if any of you end up at one of the national laboratories, you will be working on this before this is complete, if it's one of the things you wanted to work on. So with that, I'll end and take any questions.